This is a Unit 4 review for the final exam. These questions come from chapters 5 and 6. Chapter 5 dealt with systems of equations. You can see the essential learning targets here. Solve a system of non-linear equations. That's what these are. In two variables. Write the solution of a linear system with infinitely many. That's where, if you remember, we had to write the solution in terms of a parameter t. Graph the solution set of inequalities, and then we have partial fraction decomposition for chapter 5. And then we'll get into chapter 6 here in just a little bit. So starting with question 1a, this is a system of nonlinear equations. We're not graphing this, we're just solving it algebraically. This here would be a square, or a circle rather, and then a line going through the circle. So most likely going to have two solutions because a line can go through a circle twice. Now, we do not have like terms here, and we do not have like terms here. So the elimination method is not going to work. I'm going to choose to use substitution method. So if I take this bottom equation and solve for y, we have y equals negative 3x. So I can take this negative 3x and substitute it in for that y. So that top equation becomes x squared plus negative 3x squared equals 10, which then becomes x squared plus 9x squared equals 10. Combine those to get 10x squared equals 10. Divide by 10, get x squared equals 1. So x is equal to plus or minus 1. So what we have are two values of x, so we need to find the corresponding y values. So when x equals 1, y is equal to, and we have the value of y right here, it's equal to negative 3 times your x value. So if x is equal to 1, then it's 1 times negative 3, which is negative 3. So y equals negative 3. Therefore, the solution there is 1 comma negative 3. When x equals negative 1, we have y is equal to negative 1 times negative 3, which is positive 3. So the solution there is negative 1 comma positive 3. That's using the substitution method. Now for part B, we do have like terms, x squared and x squared, so we can use the elimination method. If I multiply the bottom equation by negative 1, for example, then we have negative x squared plus y equals negative 3. Now we can eliminate the x squared variable. Remember, these are not like terms, so they can't be combined into one term. You have to write it as an expression, y squared plus y equals 6. If you subtract 6, then you can factor to y plus 3 and y minus 2. So you have y equals negative 3 and y equals 2. Now we need to solve for the x values. So when y equals negative 3, now we can choose any of the equations here. I'm just going to use this equation here. So I'm going to get y, I'm going to rearrange this equation right here so that y is by itself. So I'm going to add the y over here and subtract this 3. So this bottom equation becomes x squared minus 3 is equal to y. So what I need to do is plug in this negative 3 and then solve for x. So if I plug in negative 3 for this y, then I get x squared minus 3 equals negative 3. If I add the 3 to both sides, I get x squared equals 0. So x equals 0. So the solution there is 0 comma negative 3. Now, I've got to solve again for when y equals 2. So now I'm going to plug in a 2 right here in this equation. So this is going to be x squared minus 3 equals 2, which means x squared equals 5, which means x is equal to plus or minus square root of 5. So this is interesting. When y is equal to 2, we have two different values of x. So we have square root of 5 comma 2, and we also have negative square root of 5 comma 2. So there's two separate solutions from that set of computations. So we have square root of 5 comma 2 and negative square root of 5 comma 2. So there's three solutions to this system of equations. We have 0 comma negative 3, and then we have these two. So all of the solutions, I'm just going to keep track of them here. We have 0 comma negative 3, square root of 5 comma 2, and negative square root of 5 comma 2. Okay, now for question 2, we have just a simple system of linear equations. These were nonlinear, so these were from section 5.4, solving nonlinear system of equations. Solving systems of linear equations in two variables, x and y, was in section 5.1. So what I'm going to do is use elimination method. I'm going to multiply this top equation by 2, so that gives me 4x minus 2y equals negative 20. Bottom equation stays the same. And you notice the variables cancel and the values after the equal sign also cancel, leaving us a statement 0 equals 0, which you know means infinitely many solutions. So if there are two variables, x and y, the way that our textbook handles it is to let x equal t. So we're going to let x equal t, and now we need to solve for y in terms of t. So if I take the original equation here and solve for y, that means I can add the y over here and add the 10. So it's going to be y equals 2x plus 10. But we can now make this substitution. X is equal to t. So that means y is equal to 2t plus 10. So the solution, instead of an x comma y solution, is going to be x, which equals t, and then y, which equals 2t plus 10. So both of those statements, infinitely many solutions, and then representing the solution as a set of parameters, needs to be included as your solution. I believe there's a part B with 3 variables. So we're going to use the elimination method again. Now, notice here that there is an equation with a missing variable already. Actually, there's two. This one is missing y, and this one is missing x. So one thing I would suggest is take this equation, for example, this middle equation where x is already eliminated. That means we have an equation with only y and z. If I eliminate x from these two equations, then I'll have another equation left over in terms of y and z that I can combine with this one. So just basically reduces the number of steps you have to take. So I notice that x is already eliminated from this equation. So I'm going to choose to eliminate x from the top and bottom equation, which means let's multiply that bottom equation by negative 1. So the top equation stays the same. Bottom equation changes to negative x plus 2z equals positive 7. X eliminates. we have 2y plus 6z equals 10. So I have an equation in terms of y and z that I can combine with this equation in terms of y and z. So I can take the result from that first step, 2y plus 6z equals 10, and then combine it with that middle equation, y plus 3z equals 5. And if I multiply that bottom equation by negative 2, then that becomes a negative 2y, which cancels with positive 2y. That becomes negative 6z, which cancels with positive 6z, and then we have a negative 10, which cancels with positive 10. So again, 0 is equal to 0, which is an indication of infinitely many solutions. Remember, though, if it had said something like 0 equals 10, that would be no solution. If you actually are able to solve for a particular variable at this step, like y equals 2 or z equals 5, then you would obviously go through and find the remaining other two variables. It just so happens these two were examples of solving equations for a particular, or for infinite many solutions. Now, with three variables, x, y, and z, the convention of our textbook is to let z equal t, and then you solve for the other two remaining variables, x and y, in terms of t. So this equation right here, for example, y plus 3z equals 5. If I want to get y by itself, I can minus the 3z over. So y minus 3z, or y equals negative 3z plus 5, and then I can make the substitution here. Z is equal to t. So this becomes y equals negative 3t plus 5. And now we need to solve for x. So I'm going to take this bottom equation here. X minus 2z equals negative 7. So I can add the 2z over and get x equals 2z minus 7. And then I can make the same substitution. Z is equal to t. So x equals 2t minus 7. So then our solutions is x, which is 2t minus 7, and then y, which is negative 3t plus 5, and then z, which is equal to t. So again, infinitely many solutions, and then your parameterized set of solution needs to be included as your statement. Okay. Question 3. Now we're getting into section 5.5, solving and graphing inequalities. So we have systems of inequalities here. For part A, we have a linear inequality. So we're just going to have two lines that we need to graph. So the first one, they're both in slope-intercept form. So that top inequality, 1/3 x minus 2, negative 2 is your y-intercept. The slope is 1/3, so up 1 over 3. And remember, if it's an equal to inequality, that's a solid line. So you're going to have a solid line. Now decide where to shade. So I'm going to use a test point, 0, 0. If I plug a 0 in for x, here I get 0 minus 2, which is negative 2. And over here, if I plug a 0 in for y, I get the statement 0 is greater than or equal to negative 2, which is true. So that means we're shading above that line towards the test point, because it turns out the test point satisfied the inequality, so the test point 0, 0 needs to be in the solution set for that inequality. Now, the second line here, y is less than x minus 4, negative 4 is the y-intercept, and the slope is 1, so up 1 over 1. And then, because it's not an equal to, it's strictly less than, that's going to be a dotted line. And now we need to decide where to shade. So again, I'm going to use a test point of 0, 0 and determine if it satisfies the inequality. So if I plug in a 0 for x, 0 minus 4 is negative 4. If I plug in a 0 for y, I have a statement of 0 is less than negative 4. That is not true. 0 is not less than -4. So that means I'm shading away, or the part that does not include the test point. The test point was 0, 0, and it did not satisfy the inequality, so I'm going to shade below this line not to include the test point. So then the solution set would be the portion that contains both shaded regions, and it's this portion right here. So this is the solution set. Okay. And then the other part to this is it says label all vertices. Vertices for these solution sets occur when graphs intersect. So we have an intersection point of these two graphs right here. And the way that we find the intersection point of two graphs is to solve a system of equations. So we're going to take the original system of inequalities and turn them into equations. Y equals 1/3 x minus 2, y equals x minus 4. We're going to solve this using substitution. So if y is equal to 1/3 x minus 2, that also means that this y is equal to 1/3 x minus 2. So we're going to make a substitution of this expression right here. So we have 1/3 x minus 2 equals x minus 4. So get all the x's on the same side. So I'm going to add 2 and subtract an x. So we have 1/3 x minus 1x is -2/3 x equals -2. Now solve for x. So that means I can multiply both sides by -3/2. So x equals, if I multiply this by -3/2, that's going to be 6/2, which is 3. So x equals 3. So now we need to get the y value there. So when x equals 3, I can use, for example, this equation. If x equals 3, 3 minus 4 is -1, so y equals -1. So the vertex there is 3, -1, where those two lines intersect. Okay, part B. First, we're going to graph this top inequality, x squared plus y squared is less than or equal to 25. Talked about this in class a few times. You cannot square root the left side and hope to cancel the two exponents. I saw that a couple of times on the exam. X squared plus y squared is less than or equal to 25 is a circle with radius 5, and the center of that circle is at the origin 0, 0. What we're just going to do is just make a circle with a radius 5 centered around the origin, and it's equal to inequality, so it's going to be a solid line. Well, let's try that again. Okay, not bad. Now, we got to decide where to shade, so I'm going to use a test point of 0, 0. If I plug in a 0 for x and y, 0 plus 0 is less than or equal to 25. So this is the test point we chose satisfies inequality, which means we need to shade the portion of the graph that includes the test point. So we're shading inside the circle. Okay, now the second inequality, y is greater than 2, there's no variable. So, and we talked about this also in class, anytime you have y equal to just a number and no variable, it means it's a horizontal line with a slope of 0, and the horizontal line goes through this value. So this is a horizontal line at 2, and it's dotted because it's just greater than, not greater than or equal to. So we have a horizontal line at 2, and greater than 2 means we're shading above. So we're shading above that line. Now, this one here, x is equal to a number. Well, it's less than, but if we're graphing a line, x equals to just a number, means that it's a vertical line going through this value 3. So we're going to graph a vertical line going through 3, and it's going to be another dotted line because it's strictly less than and not less than or equal to. So you have a vertical line going through 3, and then we're shading less than 3, which means to the left. So we're shading to the left of that line. So we need to find the portion of this graph that includes all 3 of the shaded regions. So we need to be above the blue line, to the left of this green line, and inside the circle. So that's this portion right here, butted up against this vertical line. So you need to be very deliberate in showing that that's where the solution set is on this. So above the blue line, to the left of the green line, and inside the circle, that'd be the solution set. Now, the vertices occur here, here, and here. So we need to find all 3 of those points, the intersection points. So again, we need to find this point, and that point. Those are all the intersection points along the boundary of this solution set. Now, this one is easy enough to locate without having to solve anything algebraically. This is on the line x equals 3 and on the line y equals 2. So if x equals 3 and y equals 2, then the location of that point is simply the point 3, 2. Now this intersection point is on the line x equals 3, but it intersects with this equation x squared plus y squared equals 25. So we know that x is equal to 3 here. So for this one, it's on the equation x squared plus y squared equals 25. It's also on the equation, though, like I said, x is equal to 3. So we can plug in a 3 for x and get 3 squared, which is 9, plus y squared equals 25. If we subtract 9, we get y squared equals 16. And now if we square root, we are going to get plus or minus 4. So we need to just choose carefully. There's only one intersection point here. Solving this system of equations is actually going to tell us that when x equals 3, y is equal to 4 and negative 4. But this intersection point in particular only happens when y equals 4. So we're only going to choose the positive value there. So that means that intersection point is the point 3, 4. Now, this intersection point occurs on the line y equals 2 and also on the circle x squared plus y squared equals 25. So we have x squared plus y squared equals 25 and y equals 2. So if we plug in a 2 for y and square it, we get 4. If you subtract 4 from the other side, you get x squared equals 21. So x equals, again, it's going to be plus or minus square root of 21, which means when y equals 2, we're here and we're over here. So this would be the positive square root of 21. This over here would be the negative square root of 21 for x. So we're going to take the negative square root of 21 as that intersection point, again, because we're on the left side of the graph. So the intersection point there is negative square root of 21, 2. So those are all the vertices of that solution set. Question 4 is from section 5.3, partial fraction decomposition. So what we're doing in question 4 is just writing the form of the partial fraction. So we need to determine how many factors there are in the denominator. So there's 1. This factor counts as 3, so 1, 2, 3, 4. This factor counts as 2, so there's 6 factors. That means 6 partial fractions. So 6 partial fractions. Each one has these as its denominators. So the first one, x, appears once. X plus 2 appears 3 times. So you need to remember what you do with repeated factors is the first time it's written to the first power, and since it's raised to the first power, you don't need the parentheses or the exponents. Second time is to the second power, and then third time is to the third power. And that power matches that power. Now this is an irreducible quadratic factor, but it's repeated. So the first time again, you write that factor to the power of 1, and then you write that factor to the second power, to where that power matches that power. Now, excuse me, each one of these are linear factors. So the numerators are constant values, A, B, C, D. Now remember, with quadratic denominators, the numerator has to be 1 degree less. So if this is degree 2, your numerator needs to be an expression that's degree 1. So EX plus F, and then GX plus H. And that would be the form of the partial fraction there. Luckily, we don't have to solve that one for the constants. Now, question 5, we're finding the partial fraction. So not only do we write the form of it, like with this one here, but we actually solve for the values of A, B, or C. For part A, there are 2 partial fractions. So you write the form of the partial fractions like that. Remember, next step is to multiply by the lowest common denominator. Then that distributes to all 3 terms. So when it distributes all the way over here to the left, the denominator cancels with this expression. When this multiplies to the A partial fraction, the x plus 4s are going to cancel. So A multiplies 2x minus 3. And then when the lowest common denominator multiplies the B partial fraction, the 2x minus 3's cancel. So B multiplies with x plus 4. Now, we need to use some convenient values to cancel A and B respectively. So I'm going to try to cancel B first by letting x equal -4. So if I plug in a -4 here, -4 plus 4 is 0. 0 times B is 0, which would leave us only solving for A. So if I plug in -4 here, the opposite of -4 is 4. And then 4 minus 37 is -33. And then here, -4 times 2 is -8. -8 minus 3 is -11. And then -11 times A is -11A. Divide by -11, and A equals 3. Now, the other convenient value here to cancel A, if we set this expression 2x minus 3 equal to 0, 2x minus 3 equals 0, you add 3 divided by 2, and you get x equals 3/2. If I plug in 3/2 here, I get the opposite of 3/2, which is -3/2, minus 37. And then here, plugging in 3/2, 3/2 times 2 is 3, 3 subtract 3 is 0. 0 times A cancels out this part of the equation, which is what we wanted. Here we have 3/2 plus 4 times B. Now, 3/2 plus 4, 4 is 8/2. 8/2 plus 3/2 is 11/2. So that's 11/2 times B. And then here, 37 is just 74/2. If we want to get common denominator, we multiply everything by 2, so that just becomes 74/2. So -3/2 minus 74/2 is -77/2. Now, if I want to isolate B, I can multiply it by 2 11s on both sides to cancel the fraction. 2's cancel. -77 divided by 11 is -7, so B equals -7. So the partial fractions now become a, which is 3 over x plus 4, plus b, which is negative 7, over 2x minus 3. For part b, we need to factor the denominator first. So w squared plus w minus 6 is w plus 3 times w minus 2. So that has two partial fractions. And as with the last problem, we multiply both sides now by the lowest common denominator. And that's going to distribute to all three pieces of that equation. When it distributes to the far left side here, the whole denominator cancels with that expression, leaving just the numerator. When it distributes here, the w plus 3 factors cancel out, so w minus 2 is what multiplies with a. And then w minus 2 cancels here, so it's the w plus 3 that multiplies with b. Now, if we let w equal 2, then 2 subtract 2 is 0, which is going to cancel a, allowing us to solve for b. So let w equal 2. 6 times 2 is 12. 12 minus 7 is 5. Here, 2 subtract 2 is 0, which is what we wanted. Here, 2 plus 3 is 5. 5 times b is 5b. So b equals 1. Now, if we let w equals negative 3, then here 6 times negative 3 is negative 18, minus 7 is negative 25. And then negative 3 minus 2 is negative 5, times a is negative 5a. Here, negative 3 plus 3 is 0, so the b part of this equation would disappear. Divide by negative 5 and you get a equals 5. So the partial fractions are 5 divided by w plus 3 plus 1 divided by w minus 2. Partial fractions was from section 5.3. Now we are getting into chapter 6, which dealt with matrices and solving systems of equations using matrices. So question A would be from section 6.2, operations on matrices. So part A would be 2 times the matrix A. So this is called scalar multiplication. Every entry in that matrix just gets multiplied by 2, so that becomes 0, 6, 4, 4. Now for part B, we have 3 times matrix B, and we're asked to add that to 4 times matrix C. So 3 times B becomes every entry in matrix B gets multiplied by 3. And then every entry in matrix C gets multiplied by 4. And then we need to check, remember when you add or subtract matrices, each matrix has to have identical dimensions. This is a 2 by 2, this is also a 2 by 2. So they can be added together, and the result, it would be adding entries in the same spot. So 21 plus 20, 3 plus 0, and so on. So 21 plus 20 is 41, rather. Negative 6 plus 4 is negative 2. 3 plus 0 is 3. Negative 12 plus 12 is 0. That would have come from section 6.2. Now, question 2 is also from section 6.2, multiply matrices. So A times B, matrix A times matrix B, here we have a 2 by 2. Matrix B is a 2 by 3. The inner dimensions there match, which means the multiplication is possible. And then remember the outer numbers here tell us that the product of a matrix A times matrix B is going to be a 2 by 3 matrix. So matrix A times matrix B is going to result in a 2 by 3 matrix. Okay, the entry here in row 1, column 1 comes from row 1, column 1. So 2 times negative 2 is negative 4. 4 times 0 is 0. Negative 4 plus 0 is negative 4. This is row 1, column 2, so row 1, column 2 now. So this is 2 times 1, which is 2, plus 4 times negative 2, which is negative 8. So 2 plus negative 8 is negative 6. This entry is row 1, column 3, so row 1, column 3. So 2 times 2 is 4. 4 times 3 is 12. 4 plus 12 is 16. This entry is row 2, column 1, so row 2, column 1. Negative 1 times negative 2 is 2. 3 times 0 is 0. 2 plus 0 is 2. This entry is row 2, column 2, so we need row 2, column 2. Negative 1 times 1 is negative 1. 3 times negative 2 is negative 6. Negative 1 plus negative 6 is negative 7. This entry is row 2, column 3. Negative 1 times 2 is negative 2. 3 times 3 is 9. Negative 2 plus 9 is 7. Now part B is matrix B times matrix A. Matrix B is a 2 by 3. Matrix A is a 2 by 2. So the inner dimensions don't match. So we would say that part B is undefined. We can't multiply matrix B by matrix A. Matrix D times matrix C. D is a 3 by 3, so this is matrix D. Matrix C here has 3 rows, 1 column, so that's a 3 by 1. So the dimensions match, so this one's possible. So matrix D times matrix C is going to result in a 3 by 1 matrix. So 3 rows, 1 column. So this first entry is row 1 with column 1. So 1 times 5 is 5. 0 times negative 2 is 0. And negative 2 times negative 3 is 6. This is row 2, column 1. So row 2, column 1, we have 5 times 5, which is 25. And we have negative 4 times negative 2, which is 8. And then we have 2 times negative 3, which is negative 6. Now this is row 3, column 1. So row 3, column 1, 3 times 5 is 15. 1 times negative 2 is negative 2. And finally, 0 times negative 3 is 0. So we have 11 there, 25 plus 8 plus negative 6, that's 25 plus 2, that's 27. And then 15 plus negative 2 plus 0 is 13. Okay, part D, B times D. So B, let's see, B times D. B is a 2 by 3. D is a 3 by 3. So the inner dimensions are match, so D is possible. And the result of that's going to be a 2 by 3 matrix. So the first entry is going to come from row 1, column 1. So we're going to have negative 2 times 1 plus 1 times negative 4 plus 2 times 3. The entry underneath that is row 2, column 1. So that's going to be 0 times 1 plus negative 2 times 5 plus 3 times 3. Now this entry here is row 1, column 2. So that's going to be row 1, column 2. So that's going to be negative 2 times 0. And then 1 times negative 4. And then 2 times 1. The entry underneath that is row 2, column 2. So that's 0 times 0. And then negative 2 times negative 4. And then 3 times 1. The entry here is row 1, column 3. So row 1, column 3, that's negative 2 times negative 2. And then 1 times 2. And then 2 times 0. The entry underneath that is row 2, column 3. So that's 0 times negative 2 plus negative 2 times 2 plus 3 times 0. Okay, now combining all these entries, we're going to have negative 6 plus 6, so 0 right there. Underneath that, we're going to have negative 10 plus 9, which is negative 1. In the middle, top, we have negative 4 plus 2, which is negative 2. We have 8 plus 3, which is 11. And then far right on the top, 4 plus 2 is 6. 0 plus negative 4 plus 0 is negative 4. And then for part E, we have matrix A, which is a 2 by 2, and matrix C is a 3 by 1. So that's not going to work. So it's undefined. Okay, solve the system using Gaussian elimination or Gauss-Jordan elimination. This was from section 6.1. This is where we need to create an augmented matrix and use row operations to reduce the augmented matrix to echelon form, row echelon form. So first create the augmented matrix. The task, remember now, and you need to follow this order, is to have a 1 right here, then a 0 here, and then get a 0 here. Then move to this entry and get a 1, then get a 0 here, and then finally get a 1 right here. That would be called row echelon form, which would allow you to solve for z, assuming the bottom row is 0, 0, 1, and then a number. Remember, the other options could be all zeros at the bottom. That means infinitely many solutions. Or if it's 0, 0, 0, and then a value here, that would be no solution. So we already have a 1 here. We have a 0 here. So now we need to get a 0 here. If I multiply this row by negative 1, and then add that to row 3, negative 1 plus 1 would be a 0, and I could call that row 3. So what I'm going to do is say row 1 times negative 1, add that to row 3, that's going to be a new row 3. So every entry in row 1 gets multiplied by negative 1, so that makes a negative 1 plus 1, which is 0. Then we have 0 times negative 1, which is 0. 0 plus 4 is 4. Then here we have negative 1 times 1, which is negative 1, plus 0 is negative 1. And here we have negative 1 times 5, which is negative 5, plus 1 is negative 4. I'm going to keep that as the only operation for that step. Now we already have a 1 here. If you recall in the problems that we've done in class, if this was not a 1, then the best row operation to do would be to multiply the entire row by the reciprocal. So if this were a 3, for example, multiply it by 1/3. Or if this were a negative 5, multiply it by negative 1/5. Multiply the whole row by the reciprocal to get a 1 right here. We already have it, so now we need to get a 0 underneath it. So if I multiply the 1 that we just created by the opposite value here, which is -4, so multiply this whole row by -4, and then add it to row 3, that's going to create a 0 right here. So we're going to make that equal to row 3. So row 2 multiplied by -4, and add that to row 3, that's going to become a new row 3. So everything in row 2 gets multiplied by -4, starting to the farthest left. So 0 times -4 is 0, 0 plus 0 is 0. 1 times -4 is -4, plus 4 is 0. 2 times -4 is -8, plus -1 is -9. 8 times -4 is -32, plus -4 is -36. Now, if you recall in the exam for Unit 4, I did say that once you get to a point in that bottom row where you can solve for z, for example, here is just the equation -9z equals -36. You don't necessarily need to go all the way to row echelon form. Technically, this should be a 1. If you multiply the entire bottom row by -1/9, you get a 1 here and a 4 here, which is exactly what we get by solving this equation, z equals 4. Now that middle row, 0, 1, 2, 8, represents the equation 0x plus y plus 2z equals 8. And if we make that substitution there, 2z means 2 times 4, which is y plus 8 equals 8. So y equals 0. The top row represents the equation 1x plus 0y plus 1z equals 5. And if we plug in z equals 4, we get x plus 4 equals 5, or x equals 1. So the solution is x equals 1, y equals 0, z equals 4. Question 4 is from section 6.3. Solve the following system of equations using the inverse of the coefficient matrix. We also call that matrix equations or matrix algebra. So we need the coefficient matrix. A matrix containing the variables, and then a matrix containing the values after the equal sign. That's called a matrix equation. The coefficient matrix here we can call matrix A. So what we need to do is multiply that by the inverse of A to cancel it, and then multiply it by the inverse of A over here. So the first task is to find the inverse of a 2 by 2 matrix, which remember is 1 divided by A times D, which is -20, minus B times C, which is -18. And then inside the matrix, A and D change spots, and B and C change signs, so it becomes +3 and -6. Here we have -20 plus 18, so that's -2, so this is -1/2. So this is the inverse of A. What we would do is, if the inverse of A was multiplied here, when you take a matrix and multiply it with its inverse, those two matrices essentially cancel each other out, or they reduce to the value 1. Like it's like dividing 5 by 5. 5 divided by 5 is 1. What you end up with is the identity matrix. If you remember our discussion from 6.3, I don't require that you show this multiplication. What you do need to show, though, is this multiplication right here, the inverse of A times this matrix. So the inverse of A here times that matrix. So if we take the inverse of A and multiply it by the matrix -4, 8, and we get the first entry is row 1, column 1, so that's 5 times -4, which is -20, and then 3 times 8 is 24. -20 plus 24 is 4. The next entry is row 2, column 1. So row 2, column 1, so negative 6 times negative 4 is 24. Negative 4 times 8 is negative 32. So 24 plus negative 32, or 24 minus 32, is 8, negative 8 rather. And then we need to remember to take this negative 1/2 now and multiply it there. So then that becomes negative 2, positive 4, which means that x equals negative 2 and y equals positive 4. Part B of this question is also from section 6.3. It's the same directions, but rather than expecting us to create the coefficient matrix, which is given here, and then find the inverse, if you remember how to find the inverse of a 3 by 3 matrix, it's a very time-consuming process, so it's already been given to us, which is nice. So really all we need to do is, with the last problem, we take the inverse matrix and multiply it by this matrix that contains the values after the equal sign. So we take the inverse of A, multiply it by that matrix that would contain the values after the equal sign, multiply that together, and that will, so this is the inverse of A, and this is multiplied by this matrix. This is exactly what we did in part A of this question, but now we're doing it with 3 variables. Nice thing about what they've given us here is they've already given us the coefficient matrix, which wouldn't have been hard to find. That just comes from that matrix there, but they've given us the inverse. So just need to do this multiplication now. I'm going to leave the 1/2 out till the end. So multiplying these two together is going to result in a 3 by 1 matrix. So this entry is row 1 with column 1. So 2 times negative 12 is negative 24. And then 0 times negative 10 is 0. 4 times 6 is positive 24. So we have negative 24 plus 0 plus 24, which is 0. The middle entry there is row 2, column 1. So we have 2 times negative 12 is negative 20. Then we have to add negative 24 rather. So 2 times negative 12 is negative 24. Then we have negative 1 times 10 is 10. So negative 24 plus 10 is negative 14. And then we have 3 times 6, which is 18. I'm going to write this all down. We had negative 24 plus 10, and then we have plus 18. That last entry there is row 3, column 1, so it's going to be a negative 24 plus 10 plus 6. And then I'm going to take the 1/2 now and multiply it into that. So we have 0. Let's see, this makes negative 14 plus 18, that's 4. Then here we have negative 14 plus 6, that's negative 8. So we have 0, 2, negative 4. So the solution is x equals 0, y equals 2, z equals negative 4. And as always, you can check your answers here. If x equals 0 and y equals 2 and z equals negative 4, it should solve every single one of these. So 0 minus 4 plus negative 8 is negative 12. Here we have 0 minus 6 minus 4, which is negative 10. And then here we have 2 minus negative 4, which is 2 plus 4, which is 6. So these 3 values satisfy all 3 equations. Finally, question number 5, find the determinant of the matrices. These come from section 6.4. The determinant of a 2 by 2 is this product subtract this product. So the determinant of matrix A is equal to 3 times 5, which is 15, minus negative 1 times negative 2, which is 2. So we get 13. For part B, the determinant of matrix B, if we follow the method, one of the methods I showed you was to copy the first two columns. And then we need all of the products going in this direction. So 2 times -2 plus, or times 0 is 0. And then we have 0 times 3 times 5, which is 0. And then here we have 1 times -4 times 1, which is -4. Now going in the opposite direction, we subtract. So that one is 5 times -2 times 1. So we're subtracting -10. And then we subtract 1 times 3 times 2, which is 6. And then we subtract 0 times -4 times 0, which is 0. So combining all of those, we have -4 plus 10, that's 6. And then 6 minus 6 is 0. So the determinant of that matrix is 0. If you remember what we talked about in class, what that means is this matrix has no inverse if the determinant is 0.